The following presentation is entitled Hidden Markov Models. Hidden Markov models play a very important role in machine learning and artificial intelligence in general. The training objectives for this presentation are to interpret a hidden Markov model, HMM, and to compute the probability of a string directly. The presentation has been structured according with these two main objectives. Okay, HMM definition. An HMM is a probabilistic model for Markovian stochastic processes systems, that is, systems whose state at time t+1 only depends on the state at time t, and only x is observed. The sequence of visited states or path remains hidden to the observer. Let's see an example. Here we have the time axis, one discrete, 1, 2, 3, 4, 5, 6. And here we have a string that will be observed. What happens with our system, which is graphically represented here, is unknown, is hidden to the observer. This is why it is called hidden Markov model. Okay, so what happens is what follows. This machine evolves stochastically in a way, in a non-deterministic way, depending on certain probability events that are governed by certain probabilities. So we will see what happens here with this example clearly. First, what happens is that the machine starts from this initial point, initial state, pseudo state, and evolves to an initial state. Could be in this machine, could be 0 or 1. Here it happens to evolve to transit to a state 0, and it emits an A symbol. So we see an A. And then the machine in time 2 moves from 0 to 0. This is done with probability 0.3 and emits a B. And then it transits from 0 to 1 in a state 3, in time 3, and emits a B. And then it moves from 1 to 1 and again emits a B in time 4. And then finally it transits from state 1 to the final state and it ends. And this is the final step of this machine. And what we observed was this string A, B, B, B. Okay, so this is the model. It's just a probabilistic model for strings. And the definition formally is as follows. An HMM is a model M, which is an ordered set including 5 elements, Q, sigma, pi, A, B, where Q, capital Q, is a finite set of elements that are referred to as states, including a special final state, capital F. Sigma, capital sigma, is a finite set of elements known as, commonly referred to as symbols or alphabet. Sigma is also called alphabet. Pi, it's a vector indexed by states of initial probabilities. A, capital A, is a matrix indexed by pairs of states. It is called the matrix of transition probabilities. And then V is a matrix of indexed by pairs state symbol, which is called the matrix of emission probabilities. So for instance, in this example we are following, we have 0, 1, and F are the states, A and B are the alphabet, A, B are the symbols of this HMM. The initial probabilities are 0.3, 0.4 here, represented here. This is not an state, this is a pseudo state. We use just to show the initial probabilities. These are the matrix of transition probabilities. Note that from each state there's a probability mass distributed over all the states where the machine, the model can evolve. So for each row we have a probability mass distributed over all states. Also, it's important to note that there's no transition probability from state F. The machine ends when it reaches state F, so there's no transition probabilities from F to another state. Okay, here we have the emission probability. So in each state there's some probability mass, unit probability mass distributed over the alphabet, which represents the probability of each symbol to be emitted when the machine is at a given state. Okay. Note also there's no emission probabilities in the special state, final state. When the machine reaches the final state, it ends, and that's all. Okay. So, what is the purpose of an HMM in this context? The main purpose is to define a probability of a string by means of an HMM. It's a formal device to distribute a unit probability mass over the set of all strings that can be built from the alphabet. So formally, the probability of a string x of length t to be generated by m is given by this equation. The probability given by m for x is the sum over all paths in the machine having length capital T of the probability m gives to x and q, the path q. It's important to know here that paths having a different length from x have a null probability of being followed to generate x because of the different length. And for this probability, by definition, the probability for this probability by definition, this is computed as follows: initial probability for Q1 for being the state visited initially in time 1 times probability of being in Q1 and emitting X1 times probability of transiting from Q1 to Q2 times probability of emitting X2 in Q2 dots, probability of transiting from Qt-1 to Qt times probability of in Qt emitting Xt, and finally times probability of transiting from Qt to F. So here we have an example. So for the HMM we are following in our examples, we have the following, and the string AB, the probability that M assigns to the string AB, it's the probability that M assigns to AB following the 0,1F path plus the probability that assigns to AB following the 1,1 path. Note that, well, I go back. Note that AB can only be generated following with positive probability following the path 0,1F or 1,1F. So this is why there are only two paths with positive probability to generate AB. First one is this one, which is 0,1 AB, which is this value, which is 0.6 times 0.5 times 0.7 times 0.8 times 0.4, which is this term, which is this value. And then this is the other path, 1 and then 1 again, and first we emit A and then B, which is this probability, which is 0.4 times 0.2 times 0.6 times 0.8, and then finally times 0.4, which is this value. And if we sum everything, it is 0.08 to 56. So it's an 8% approximately of probability of generating this string, or the probability assigned to the string AB by this model. And to conclude, we have seen what an HMM consists in, and we have also seen how to directly compute the probability of a string to be generated by an HMM. And this ends the presentation.